an email, or I posted it in Blackboard, but you got an email about this as well. But it was after I saw you, but the Math Help Center is open now. That's the math department's tutoring service, or one of them. There will be another thing maybe next week or the week after to get started up. I'll let you know about that. But in the meantime, these are our student tutors. So here's the schedule. This is posted in Blackboard as well. Same place the syllabus and everything is. Monday through Thursday, afternoons and evenings, right? So 4 to 7 a couple of days, 4 to 10 a couple of days, but that's the schedule. That's in Norris 104, which is, Norris is the next building over that looks like this one on that side of the building. And basically this is just drop in, like they're there to help. So that's, a good place to go work on homework or whatever, so you can ask questions as they come up, that kind of thing. There's also, not that you need it, but there's another link there to my YouTube channel. You have that elsewhere as well. But and these should be hanging up around the building soon. I don't think they are yet because it just went out yesterday afternoon. But so one more time, that's in Blackboard. Soon they'll be hanging up. If you have any questions, let me know. But take advantage of that. You've already, it's free to you. You've already paid for it, I guess, depending on how you want to look at it. But there's no additional charge or anything. Just go, drop in, ask for help. Yeah, that's there. And I would, advise with any kind of tutoring thing, like just make it part of your routine to, pick a couple times a week that you're going to drop in and do some stuff. And then the last minute get ready for the test thing won't be that big a deal if you, are just consistent and sort of stay ready. Okay. All right, so yesterday I don't know why I wrote all this stuff down just to show you the schedule. Yesterday we talked about transforming graphs and vertical and horizontal shifts and kind of how that works. Again, big idea is that stuff happening inside the action of a function, whatever that is, inside a square root, inside a square, whatever, inside the parentheses if you want, keeping in mind that sometimes they're implied rather than actually written. That affects x values. So something like adding a 3 inside this square here shifts the whole thing to the left, right? X values are x is the horizontal axis. So that's going to change those, and does it by moving it to the left. Something like this, x squared, then plus 3, right? So the plus 3 happens after the square does, yeah. Oh yeah, right here. Happens after the square does, so it's sort of at the end or on the outside. That affects the y values sort of directly, moves the whole thing up, right? Because what you're doing is taking all the y values and making them 3 bigger than they used to be. Well, it's going to sit up higher, right? So what it appears to do is sort of shift up. So that's the very quick version of what we talked about yesterday. And then I asked you to work 7 through 10 on the back, or at least give them a shot. We're going to take the next 10, 15 minutes for you guys to talk in your groups and compare notes and see what you came up with. I will, wander around and talk to you, and then we'll talk about it all together. If you're not already, a lot of you rearrange furniture already, which is great. The rest of you do so now. You guys in the back, move so that you can face each other and talk. All right, so let's just kind of work through those, talk about those all together, see what we think. So y'all tell me about this first one, 7. Okay, so the parent you said is a quadratic. That means x squared. If the word quadratic freaks you out, don't worry about it yet. Like, we can wait a couple of weeks before we have to worry about that part. But y equals x squared, because, again, kind of the way we recognize that is if I take out or ignore any like -1, +3, that kind of stuff, small changes like that, what's left is the squared, right? The x squared part of it. So that's the parent function. That's the thing that does most of the work in determining what this thing is actually going to look like, right? It's x squared. So what does a square function look like? What does its graph do? U-shaped graph like that, right? Again, or called a parabola if you want, but looks like that. Where does it live in the plane? Where is it? By default, no, ignoring the -1, +3 and stuff. Where is it? Sitting at the origin, right? The point at the bottom of it, the one that's easy to tell apart from the others, sits right on the origin and it opens up, right? Okay. So that's our parent function, y equals x squared. Again, that looks like this. All right. Now, y'all go ahead. What else? What happened to it? Over 1, up 3, over which way? To the right 1. That's that part. And up 3. From the +3 at the end there, right? Okay, so x squared shifted to the right 1. That x minus 1 inside the square, right? Inside the parentheses or inside the action, what the function does. That affects the x values directly, so it moves it or appears to move it left and right. And again, it kind of feels backwards, right? It kind of feels like the opposite of what it should do. You're subtracting, that moves it to the right, but that's the positive direction. But think about it as making everything happen later, right? That's what's going on. So it shifts to the right, and then the +3 at the end on the outside, right? After the square happens, picking order of operations, right? Parentheses first, then exponents, then the addition last. That +3 at the end is going to make everything sit 3 higher than it did, so it appears to move up 3. So what we get, I didn't ask you to draw this one, but what you would get is this same shape of graph, but sitting to the right 1 and up 3. So that base point that used to be at the origin, where is it now? One, 3. And I can just draw it in, right? So again, that point is easy to keep track of as we move it. And then the others I just kind of sketch in the homework in MML. I didn't look, I forgot to look this morning, but I think the graphic tool has you like select that point and then give it one more point. So what you would do is just figure out like what the point next to it is. All right, so you can like plug 2 into that and figure out what it is. That would be it. Or 0 or plug some other x value into that and get a point that goes next to it. We can talk about that some more later if we need to. Okay, everybody on that? Everybody agree? Questions? Okay, cool. All right, we can do a little bit quicker version of the rest of these. Y'all tell me about 8. Describe and sketch the graph. So let's just kind of do the same thing. What's the parent function? And then what's happened to it? Yep. So it's a square root, right? Because again, if I ignore the +3 and the -2, what's left is the square root part. What does the square root function look like? Well, sitting sort of tucked into the corner in quadrant 1, right? And going that way, right? Little curvy, hooky kind of a thingy. All right. And what happens to it? So there's a +3 on the inside, which is going to move it 3 to the left. Yeah. So it is a left-right. It's a horizontal thing, right? But it's actually going to move it to the left. And then down 2. And of course, we could always, keep in mind you've got a calculator, right? X plus 3 minus 2. Even if I look at the thing and, see that plus 3 and think like, okay, well, it moves to the right. If I graph it, this gives me another check on that. Because what did the plus 3 actually do? It moved it to the left. So I go, oh, right. Yeah, that's the one that works backwards. Right. So, use this as a way to, both help check and help kind of frame the way you're thinking about things. Right. Tying the equation, symbolic representation of the thing to the graph. I think tying those two things together, the quicker we can do that, the better off we're going to be. So, move to the left 3 and down 2. That point that used to live at the origin, now it's at -3, -2. Okay, write down the function whose graph is shown here. So what do we need to do to be able to do that? We have to figure out what kind of function it is, right? What the parent function is based on the shape of the thing, right? So I got to figure that out. What type of function is this? And then once we've done that, I got to think about, okay, well, where does that live and how is this different? Okay, so you guys in the back, what kind of function is it? X squared, right? It's a parabola. It's x squared is the parent function, right? So whatever we end up with, it's going to look something like this with maybe some stuff here and here, added or subtracted, as needed. You okay with that part? Okay. Now, x squared lives right here normally. So what has to happen to get it from there to where it is now? You got to go to the right and then down. How much? 2 to the right, down 3. Okay, how do I make it go 2 to the right? -2 where? Inside the square, yep, -2. And then down 3? -3 outside. Once you have a thing that you think works, you can't start with graphing it in the calculator because I gave you a graph and you can't feed in a picture, right? But once you have a thing that you think works, we can check. Yeah, okay, that looks right. If it was in the wrong place, hopefully it's just like one of the things that I have to fix so I can figure out how to correct it. If it's the wrong shape of the graph, well, hopefully I can correct that, right? Like if I'd gone with, x cubed. I might say, okay, well, that's in the right place, right? The point that used to be at the origin, now it's at 2, -3. So that's in the right place. So I did the shifting part right, but the cube part must be wrong because it's the wrong shape. So I can, fix that. Okay. All right. And then the function whose graph has the same shape as the absolute value of x, but shifted up 2 units into the left 6. Absolute value of x plus 6 plus 2. Good. And then again, you could check that if you wanted to, right? Good. Perfect. Okay. Is everybody feeling, again, sort of medium comfortable with this? You've done like 4 problems, so, you shouldn't be totally comfortable until you've actually gone through a bunch of homework on your own, but we feel okay for now anyway. Okay, we can work with okay for now. All right, so that's how shifting works. You add or subtract something. What you do is basically pick the graph up and sort of slide it around, but like preserve the shape. Other things that we're going to look at are, again, kind of like minor, relatively changes to what happens. So it's, we talked about what happens if you add or subtract something. Now we're going to look at, okay, what happens if I multiply? If I multiply it by 2 or -1 or something like that. how does that affect things? Again, I want us to kind of think about, taking the graph of the sort of original thing, like the function that's actually sort of sitting there doing the main work and determining what the thing looks like, and looking at kind of how it changes or moves that around. So again, similar to what we did yesterday, there's a, oh, I don't even have the notes downloaded. There's a QR code there at the top with a Desmos graph that has some stuff. There we go. To again, sort of, spend a few minutes just kind of fiddling around with and trying to figure out, what these things do. Okay, so far we've been looking at what happens if you add or subtract something somewhere, right? So add or subtract a constant value. Now we're talking about multiplication, right? So I take this function and multiply by something, what happens? I gave you a little bit of a nudge in terms of like language you can use to talk about what's going on, right? But here's the square root of x, that dashed line, that's the starting point, the original function. And again, let's just kind of look at these things one at a time. So the first one, y equals negative square root of x or negative f of x, right? Whatever the function is. I can think of that first thing as being just its opposite in terms of the sign. What happens? What did that do to the graph? Flipped it how? Over the x-axis, right? Think about, I mean, this kind of goes along with the symmetry discussion we had last week. It flipped it upside down, right? But a more precise way to say that is that the x-axis is the thing that stayed put, and we reflected the whole thing or flipped it over that line. So what you end up with is a graph that, anywhere it hits the x-axis, those points stay put, right? The point at the origin there that's on the x-axis, it stays where it was. The rest of it though is upside down. Or if you want to take it to the level of like coordinates on the graph, let's see, this is a square root, so it goes through like 4, 2. There's 4, 2. Negative square root of x, well, the square root of 4 is still 2, but then you flip the sign, so it's negative 2, right? So 4, negative 2. So every point up here is up down here, and vice versa. This one didn't have anything that lived underneath the x-axis, but those would. I'm good. Nobody worry. So the whole thing reflects, but it reflects more, a little more precisely over the x-axis, right? It's upside down. How can we tie that idea back to this stuff that we've been talking about with things happening inside and outside? You add or subtract something on the outside, what happens? Moves up and down, right? It affects the y values, shifts things vertically. Where is that negative sign happening here? Outside, right? It's out in front of the root. And how is it flipping the thing? Over the x-axis, so flipping it over vertically, right? So it's still, we can still think of it as affecting the y values, right? Okay, so if thing happens outside, it changes things from a like vertical y value kind of perspective, right? Now, when we talk about that, the x-axis is the thing that stays put, right? So it's reflecting over the x-axis, but that means it's upside down. All right, what does the other one do? Now the negative sign, we're taking the opposite inside the function. What does it do to the graph? Reflects it over the y-axis. So it flips left for right. So instead of upside down, now we're going a left-right reflection, flipping over the y-axis. So again, it's a thing happening inside the function, and what it's affecting is you know, sort of an X value kind of thing, right? It's affecting the left and right. Okay, so changing a sign, taking an opposite like that is a reflection either across the x-axis, so upside down, or across the y-axis, so left, right. Does it matter that it was the square root function that we're doing this with? No. Yeah, just like before. For any other function, it's going to work the same way. So there's x squared, negative x squared. Oh, sorry. Forgot that those weren't set up the way I thought they were. Negative x squared is, well, x squared, but upside down. What would this be? What happens if you take x squared and reflect it over the y-axis? It's the same because it's, and we call those even. So it's a reflection this way, but for that particular function, you just happen to get the same thing back because it's an even function, right? Okay. All right. What does this, sorry, let me get this back to where it ought to be. That's what I get for going off book. What does multiplying, so the last one there, c times the square root of x, what does that do? Well, here c is 1, so it's not changing anything. I guess. What happens if I multiply by 3? Makes it taller, makes it steeper. I, suggested thinking about it in terms of stretching or shrinking. Stretching or shrinking in what sense, though? Like if I'm going to think about that as taking the original graph and either stretching it out or shrinking it down, how's that working? Or maybe where does that factor of c, so this is 3 times the square root of x that we're looking at right now in purple. Where is that factor of c showing up? On the inside of the function or the outside? Outside. Okay, if it's outside, what should it do? Affect the y values, right? Up and down. Okay, so imagine that you had this graph, the square root, the original one, on, like silly putty or like a rubber sheet or something. If I multiply by 3, what that does is make all of the y values 3 times taller than they used to be. So it's like I took that sheet of silly putty that I've drawn this graph on and grabbed it by the top and bottom and stretched it out so that it was 3 times as tall as it used to be. What's the graph going to do? Well, it's going to go like this, right? It's going to get taller, steeper, everything's going to sort of happen faster, right? Because it's going to get stretched out this way, the thing's going to go up along with that. Okay, what if instead of 3, it was like a half? Now, instead of stretching it out, it's like I'm compressing it or shrinking it down, right? And again, if I've got it drawn on, something like silly putty or whatever, what that's going to do is make the whole thing kind of flatten out, right? It's sort of squishing it down, so it's going to look shorter like it does there. So instead of stretching it out, we're shrinking it down. Okay, and again, that doesn't matter. It doesn't matter that it was this function that we started with. The same thing happens for any others as well. If you multiply by something on the outside, it's either going to, depending on how big that number you're multiplying by is. If it's 1, that's no change, right? So if it's anything bigger than 1, it's going to appear to get like taller, right? If it's anything smaller than 1, it's going to appear to get shorter. Okay. We're not really going to get into if you multiply by something on the inside. The idea is the same. It's just that you would do it from the x, from the horizontal perspective, sort of stretching out and shrinking. The problem is that if you kind of think about it, this idea of stretching it out vertically and the thing getting taller, the same kind of thing would happen if instead I grabbed it by the sides and sort of squished it in, right? It would do the same kind of thing. So just to sort of simplify things and not have to worry about like, well, is this taller or is it squished in this way that's making that happen? We're just going to sort of only do one of them, right? So like it exists, and if you multiply by something on the inside, it works the way that it seems like it should, that it's going to be a horizontal stretch and shrinking kind of thing. We're just going to try to simplify things a little bit. If you go on to pre-cal, you'll see that come up again there. Okay, so to sort of summarize everything. Stuff that happens inside affects X values, right? So left and right. Either by moving, right? Shifting if you're adding something, or by reflecting this way over the y-axis, or by if it was a stretching shrinking thing, which again, we're gonna not really get into, but it would be a stretching shrinking thing from the X value perspective. Stuff outside affects Y values. So up and down. If you're adding or subtracting, it's moving stuff around. If you're changing a sign or taking an opposite, like multiplying by a negative, it's a reflection. And if you're multiplying by, so if you're scaling it somehow, like multiplying by 2 or by half or something, that's going to stretch and shrink things. Okay. So hopefully you kind of start to see why I don't think this should be a thing that you try to like break down into like plus A times C and like memorize all of those, because there's too much of it, right? There's like at least 6 different things there that are happening then. You got to remember like this does that. Think about, where each of these things is coming from and what it's going to do. So if I look at like this, y equals 3x squared, what is happening there to change the function x squared? What's different? Multiplying by 3. Okay. Multiplying by 3 inside the square or outside? Order of operations stuff. What should happen first there? The exponent, right? So the square happens first. So the multiplication's outside then, right? Because it happens after. Okay, so this is times 3 happening, what we've been calling outside. Okay, it happens outside, so it's a vertical thing. And what does multiplying by 3 do? Does it move it? Does it flip it? Does it make it taller or shorter? It's going to be a stretching thing, right? So stretches vertically by a factor of 3, right? Times 3. So if you're going to compare that to the original, say that's x squared, this is going to look something like that. It's going to sit in the same place. It's just going to be like 3 times as tall. So that point at 0, 0 doesn't move because 3 times 0 is still 0. Everything else is just going to be 3 times taller than it used to be. That kind of make sense? Okay. So what happens with the one next to it, number 2? So it's x squared again. You're multiplying again on the outside again, but now you're multiplying by 1/3. Well, 1/3 is smaller than 1. So everything is going to be sitting lower than it would otherwise. So the whole, we'll call that a vertical shrink, but it's just going to look, sort of shorter, slower, wider, whatever. The whole thing's going to sit down lower than it did before. So again, if I graph that on here too, it's going to sort of sit in the same place, but something out like that. Okay, makes sense? You have any questions at this point? All right, so you guys talk about 3, 4, 5, and 6. All right, somebody tell us about 3. First, what kind of function is it? Absolute value. And what does an absolute value function look like, or the graph of an absolute value function? V, right? V-shaped graph, sharp corners, straight lines, opening up. Okay, so it's that. And what does that negative sign out in front do to it? Flips it. How? Reflects across the X or the Y? X. Because what should happen is that it's upside down because it's happening on the outside. Right? So it should be changing Y values. It's flipping upside down. The way we talk about flipping upside down is to say that it reflects across the X-axis. Right? Okay, so upside down is the thing you think. Reflect across the X-axis is the way that you actually express that, right? To be like precise about it. Okay, what about 4? What kind of function? X squared. And what happens to it? Reflects across the X-axis. Okay, good. 5 and 6. We got a square and a cube. That negative inside reflects across the Y-axis, but I heard somebody say something about it being the same. Why? Because it's x squared, right? This is the same thing as that. You take negative x and multiply it by itself. What happens to the negatives? Cancel, right? You just get x squared back. Because it's an even function, right? So it does this wax reflection, but when you do that, you end up with the same thing that you started with because it's even or because that negative would sort of cancel out, right? What happens in 6? Similar sort of thing, right? Negative x cubed, so multiply 3 copies up, is negative x cubed. Okay, well, what that does is reflects across the x-axis. Sorry, the y. My bad. But this fact says that that's the same thing as reflecting across the x-axis, right? Because x cubed is what kind of a function? Odd. So now we get a little bit more insight into like what the symmetry stuff says, right? Hopefully that, you know, that thing about like f of negative x being the same as negative f of x, that's just this, right? Same as negative x cubed because x cubed is odd. So it still reflects, like it's going to look different than x cubed did. It's going to reflect. It's just that you could get that same picture, that same reflection by doing this or by doing that because it's an odd function. Okay, so homework for Thursday is the back. Same deal as last time. 7, 8, 9, 10. For Thursday, we will spend some time going over those. One kind of word of warning with these, write down what you think is going to happen, then check, especially like the first couple, write down what you think is going to happen, then check it with the calculator or Desmos and see if those things match. Putting all of these things together and doing them all together at once, there are a couple of like little things that we got to sort of be careful about and look out for. All right, so think about like order and how things are, you know, going to all sort of work together. Again, try them all, see what you come up with, think through them. Thursday, we will pick up with that. I'll also have some other stuff for you to do on Thursday.